I'm Austin Monell, and this is my electric skateboard. So I'll first go over the main components that I made this out of. So the board in the back truck is a mountain board, which I had laying around, which I never used, so I decided to make an electric skateboard out of it. This piece in the front, including the wheel and the base plate, came from a kick scooter. And a kick scooter, just basically you kick a back peg and it converts that linear motion into rotational motion, which moves a chain and spins a sprocket, which spins the wheel. For this piece, I ended up changing out the sprocket with a larger diameter sprocket so the gear ratio would be right, because if I used a smaller sprocket, I wouldn't have nearly as much torque as I do with a bigger sprocket like this. Also, this was originally a one-way bearing, and what I ended up doing is welding the bearing together so it's just fixed to the shaft, because for this I don't want a one-way bearing. And originally on the scooter it had a one-way bearing because when you kick you want it to rotate the wheel, but when you're not kicking you want it just to be able to coast along without moving the whole sprocket. This motor came from one of those mini electric dirt bikes, which is made for kids, but I had one laying around, so I ended up salvaging the motor out of it, which is a pretty simple DC brushed motor. And originally I used this 5-cell 5 amp hour battery just plugged directly into the motor leads with a big switch in series. This is the switch I used. It's a deadman switch, so you click it, it runs the motor with the switch in series, and when you stop clicking it, it just turns off the motor. Eventually I realized that this isn't a good idea because it's really inefficient. For one, I'm running this whole thing in series, so the power has to travel through the whole length of this cord twice because it's in series, which creates a lot of resistance, which is inefficient. But also, it wasn't good just because I couldn't vary the speed, which is essential when I'm getting going and then when I'm slowing down. So I ditched this idea and used an ESC, an electronic speed controller. This is one that is made for DC brushed motors, and it can go up to 30 volts at 80 amps, which is plenty to run this motor. And to vary the speed, I ended up using a Spectrum DX2E transmitter. This is usually made for RC boats or cars, but the throttle stick works excellent for this application. Also, I don't have to hold a big wire to control the speed. This just transmits a signal, and I have a receiver for it right here, and this sends out a PWM signal. But the problem was I couldn't just directly hook this up to the ESC because the PWM protocol is different than what the ESC takes. So I ended up using an Arduino as a PWM protocol converter. So I'll go over how the PWM protocol works and what kind of signal I get out of this and what kind of signal I convert it to the ESC. But basically, this is just connected through the signal to the ESC, which controls the speed of the motor. You might ask, how am I powering the receiver in the Arduino? And I'm actually just using 2 of the cells from the main battery, which is enough to power the Arduino, which is 8.4 volts when it's fully charged. And I just use this lead right here and plug it in to the balance lead of my LiPo battery. This also powers the fan cooling the ESC when it gets hot, and that's basically in parallel with the board, which powers the receiver. You can see that I've spread out the antennas for my receiver to get the best polarization possible when I'm riding it. I don't need too much just because I'm right next to it, but it's always good to separate your antennas so you can get the least amount of interference as possible. To secure the battery, I'm using a metal screw strap, which has a rubber coating on the bottom, which prevents the metal strap from piercing the battery, which can be really bad because these things will explode. So you always want to power up your transmitter first to prevent external signals from various devices around from interfering with your receiver, which could cause the motor to spin up randomly at any time. So after the transmitter is powered on, we can plug power in for the fan in the Arduino, which powers the receiver. Now that both these are on, I can finally plug the main power, and that powers the ESC. So with the simple pull of the trigger, I can control the speed of the motor. This ESC has a special function called braking. See, if I push my throttle stick forward, the red LED goes on. What this does is basically shorts out the two leads from the motor, so that when it tries to spin up the motor has resistance, because when those are too shorted out, it can't send the power anymore, so it just creates heat in the motor and resists the coils in the motor from spinning, which in turn slows down the shaft, slowing the wheel down, as you can see. I can brake it whenever I want it. Just for emergency, I have a manual brake too, which just locks up the two rear tires. After testing this for a while, I soon realized that it doesn't have enough power to go as fast as I want. It has enough torque, but not nearly enough speed. To fix this, I could either change the sprocket size, either make this one larger or this one smaller to increase the speed of the wheel, or I could just up the voltage of the battery, which the ESC can take, which will spin the motor faster. So lithium polymer battery, each cell has 4.2 volts when it's fully charged and 3.6 volts when it's safely discharged completely. This means a 5-cell lithium polymer battery has 21 volts. This ESC can take up to 30 volts, so I could use up to a 7-cell lithium polymer battery, which is 4.2 times 7, which is 29.4 volts. Unfortunately, there aren't too many 7-cell batteries out there that are just one component, so I had to make my own. To do this, I just took this battery, which is a 5 amp hour 5-cell, and I took two 2-cell 2.5 amp hour lithium polymer batteries that I had laying around and wired them in parallel, so it increased the capacity, so that would create 5 amp hours, which is equivalent to the capacity of each of these cells. And I ended up creating a connector that went in series with the connector on this 5-cell, so that makes 2 cells plus 5 cells, and that makes a 7-cell battery. So now that I have two 2-cell batteries wired in parallel, which are in series with a 5-cell battery, which basically makes a 5 amp hour 7-cell battery, which is around 29.4 volts fully charged. I'm nearly maxing out this ESC, so it should go a lot faster. That's definitely a lot faster. Okay, so as you can see, I have a nice paint job here with 2 pieces of grip tape so I won't fall off the board when it's going around 10 to 15 miles per hour when I have a 7-cell. Alright, I think I'm ready to ride it. This is my circuit schematic of the electric skateboard, and as I said, all it does is convert the PWM signal coming from the receiver and converts that to the PWM signal range that the ESC can take. To start off, you'll notice my Arduino Uno and the 7-cell battery, and you can see that 2 of the cells of the 7 cells of the battery are hooked up to the voltage in and ground of the Arduino. This is also powering the cooling fan of the ESC, which is right here. And that's connected to, you can see, the positive terminal and the ground terminal of the Arduino, which is connected to the negative terminal of the 2nd cell of the LiPo. You can also see that the LiPo is also connected to the main negative terminal of the ESC, and the other positive end of the battery is connected to the positive terminal of the ESC. The positive terminal of the battery is also connected to the one end of the motor, because this ESC controls the power output that goes to the motor in series, where you can see M out stands for motor out, and that goes to the motor, and the ESC controls the power output of M out. You'll notice that the signal end of the receiver goes to digital pin 2, and the positive and negative terminals of the receiver goes to 5 volts of the Arduino and ground of the Arduino. Also, the positive negative terminals of the ESC, of this side of the ESC, go to 5 volts of the Arduino and ground of the Arduino. And the signal of the ESC goes to digital pin 3. So the only pins that we're using on the Arduino is 3 to control the ESC and 2 to receive the PWM values of the receiver. Just to recap, this is a 7-cell lithium polymer battery, as you can see, that has 5 amp hours and can discharge at 30 to 40 C, which means that it can discharge 40 times its capacity, which is 5 amps. So 5 times 40 is equal to 200, so its maximum discharge rate is 200 amps. Multiply that by your voltage, which is a 7-cell. Each cell is 4.2 volts. You get 29.4 volts. 200 times 29.4 is 2100, which means its maximum power output is 2.1 kilowatts. Okay, so this is my program explanation. So as you can see, code. So we got my comments, circuit explanation, program explanation, what I'm about to do. Okay, so right here, these are initializing my integers. So we got the ESC pin input, which is digital pin 3, and then we got the ESC value, which is the value coming from, or going to the ESC, and then the throttle integer, which is digital pin 2, and that's the input pin, which is the signal from my receiver is going to, and the value of that. If we go down into the setup, we got pin mode setting the throttle pin as an input, and then right here I'm just beginning my serial communication. If we hop down to the loop section, I'm using the function pulse in, which reads the distance between the high and low pulses of my PWM signal coming from the throttle channel of the receiver, and we're making that equal to throttle value. So now I have a variable throttle value equal to the PWM value of the throttle channel of my receiver. And right down here, we're converting this throttle value into a range that the ESC can take, and we're setting that equal to the ESC value. And right here, this line is for the basically the course. So right here, this line is my fine tuning, if you will, of scaling the throttle value into the ESC value. Then down here, I print the values of the throttle valve, which is the raw values coming from the receiver, and the scaled value of the ESC, and then I just print space between the lines so we can visually see it. And then finally right here we have an analog write, which basically means PWM write through a digital pin, and then ESC is the pin that I want to write to, and ESC val is the value I want to write to the ESC to control the throttle. And this delay right here is not necessary for the code. In fact, it might ruin the code if I put this in. This is just so we can visually see the printouts of the values. This would cause lag in response to my throttle input of the transmitter, because it'd be delaying each time a value is sent. And if we go over to my serial monitor, we can see the real-time values coming from the throttle channel and the values being sent to the ESC. The scaled throttle value, the reason that that's not 0, it's averaging around 177, 178. That's because the ESC is calibrated to start the motor when the value is around this range. And the reason that the raw is so much higher than the scaled is because the value coming from the receiver, its PWM rate is a lot faster to decrease latency time, which is basically delay in response to my stick movements of the transmitter. And the reason that the scaled value is so low is because that's just what the ESC takes. And when I pull on the stick to control the throttle, you can see it increases to around 250, which is about the maximum that the ESC can take. And you can also see the raw value goes up too. And then when I go back to neutral, it goes back to what it was. And when I go into reverse or braking in my case, it decreases the value, as you can see. And then neutral again. And that's basically what controls the motor. Alright, that's about it for the electric skateboard. I hope you liked my little montage of me riding the skateboard around my street. As you can see, it goes pretty fast, and definitely a lot faster than walking.